All right, so domains all reals. Does this thing, does it have any symmetry? Does it have odd or even symmetry? Just type your answer in chat. What's the verdict? Everybody weigh in on the symmetry. I'll give you a hint. The correct answer is already in chat somewhere. Let me ask you this. If I were to evaluate this function at negative x, would anything change? It wouldn't, would it? Everybody agree that f of negative x is the same thing as f of x? Because only one x appears. It's right there, right? And if I substitute a negative x there, well, the quantity negative x squared is the same as x squared, isn't it? So this is even symmetry. And that's true because f of negative x equals f of x. Okay, so we have even symmetry. That's helpful, right? We have folding symmetry about the y-axis. Okay, so now we need to do some, we have to find inflection points, and while we're at it, let's go ahead and do everything. So we got to differentiate. So what's my derivative going to be here? This is a chain rule, isn't it? I've got the log of hand. The derivative of log hand is what? Derivative of log u. We'll just call it u. Derivative of log u is what? Right? You got to remember that one. That's u prime over u, right? Everybody agree? We've got here's our derivative rule that we're using. Right? Derivative of log u is u prime over u. So what's that going to give us then? We're going to get the u prime is just going to be 6x divided by u is 3x squared plus 1. Agreed? Okay. All right. So then are there any zeros of the first derivative? Yeah. X equals 0, right? Nowhere is the first derivative undefined, though, because the bottom is never 0. So we do have a critical number here. At x equals 0. Let's take our second derivative. Second derivative, we've got to use quotient rule, right? So I've got low d high minus high d low. Derivative of the bottom is just 6x, right? All divided by 3x squared plus 1 quantity squared. And if I distribute the 6 on the top and collect like terms, I'm going to get 18x squared plus 6 minus 36x squared. So that's just 6 minus 18x squared divided by the quantity 3x squared plus 1 squared. And if I want to factor out a 6, I could do that, right? So I get 6 times 1 minus 3x squared over 3x squared plus 1 squared. So are there any zeros of the second derivative? Yeah, there would be, right? The second derivative is 0 when 3x squared equals 1. Everybody agree? So x would equal plus or minus 1 over the square root of 3. Everybody agree? Or square root of 3 over 3 if I want to rationalize that. So we've got all the magic numbers that we need then. Or we got all the critical numbers, and we know the zeros of the second derivative. So now we can make our table. Okay, so we had first derivative critical number at 0. We had second derivative critical numbers at 1 over radical 3 and negative 1 over radical 3. And we know we have to because we have even symmetry too, right? So we know that this thing's going to fold about the y-axis. I have to get symmetrical parts on the left and the right side of my graph, don't I? Okay, so those were zeros of second derivative. Now what? Let's see here. Lily, what should I probably do next?
You have to find points in between, right?
Yeah, we're gonna have to test something, aren't we? Right. But we want to know, we're going to work as far down as we can, correct? So we'll work in the second derivative row here. So what point should I evaluate the second derivative for first? Okay, I'm seeing zeros. Good, right? We want to use the second derivative test. We want to know what's the sign of the second derivative at this 0 of the first derivative. Right? If I have a 0 first derivative, let's remember what that means. That means we've got a horizontal tangent line there, right? And we need to know what the sign of the second derivative is. Well, I've got it in a nicely factored form right there, don't I? So if I want to evaluate that at 0, what are we going to get out of that? So we know f double prime of 0 is going to equal, the top is going to be positive and the bottom's positive, right? So we get a positive second derivative. Well, then that means it's concave up. Horizontal tangent plus concave up equals minimum, right? So we got a minimum at x equals 0. Now, okay, Lily, back to you. So give me an example. What would be a test value I'd want to pick here?
Could you use like -1 or 1?
Sure, I could use, how about 1? So if I use 1 for a test value, if I evaluate the second derivative at 1, I'm going to get 6. That's going to be negative, isn't it? 1 minus 3 is going to be negative. So I'm going to get negative over positive is negative, right? So that's going to be negative. And so this is an inflection point. So I know that this has to be also because I've got symmetry, don't I? Okay, and I could check at -1. I'm going to get the same result, aren't I? I'm going to end up with a negative second derivative, and so I get an inflection point there. So what did this question ask for? They want to know the intervals where the function is concave up or concave down. So it's concave up on the interval where the second derivative is positive, right? If we wanted to sketch this thing, let's even just do that. Let's do that first, how about? So if I want to sketch this thing, here's my y-axis. If I plug in the point 0 into my original function, I get 0. So I have a minimum at 0, 0. And I have an inflection point at 1 over the square root of 3. I don't want to figure out what that is. Oh, actually, that wasn't 0, was it? Oh, yeah, it was. Yeah, it was. Right? If I plug in 0, I get the log of 1, which is 0. If I plug in 1 over the square root of 3, oh, that's going to work out okay. I just get log 2. So I get the ordered pair x equals 1, or x equals 1 over radical 3, y equals log 2. Same on both sides. So I'm going to get an inflection point up here. And then this thing's just got to do this, doesn't it? It's a minimum. And then here it's going to turn over. So it's concave down to the left of that inflection point, the right of this one, in between the two, it's concave up, right? So there's my picture. If we want to know the intervals on which the function is concave up, it's just going to be here, isn't it? Between negative 1 over radical 3 and positive 1 over radical 3. And they probably want you to rationalize those denominators. That's fine. And it'd be concave down on the other intervals, right? So concave down on, for all values of x less than negative 1 over radical 3, or, and I don't know if they tell you to use commas. They probably just use commas, I'm guessing. But if not, you'd just use the union operator for or. There it is. Okay, makes sense? Other questions? Kyle, did you come up with one?
I just needed to see another example in general. I think I'm good.
Okay, so that one works. Okay. All right, let's look. We're getting, I mean, we've gone through a ton of these things, but I think there's, we left off on this guy, right? I think this is where, yeah. Okay, this is, we'll just look at one more of these rational functions. Did we do one? Okay, so we got two more. These are pretty quick ones though, but I want to go through both of these because there's some stuff on these that we still haven't talked about. So what about this one? So we know that the domain, we have to exclude the values -1 and 1, right? We already did that. We know this is an odd function because the top is odd and the bottom is even, right? Or you can just do the test for symmetry and you'll prove to yourself that it's odd. Okay, we took limits here too, right? Remember, we reviewed our limits of rational functions, and in this case, because the denominator is a higher degree polynomial than the numerator, the limit as x approaches plus or minus infinity is 0. Okay, another way of looking at that, though, and this is the way, honestly, I prefer to look at it, is I just look at if they're rational functions. You can just replace the rational function. If we're looking at the tails of the function, we're approaching positive or negative infinity. The behavior is going to be the same as if I only focus on the dominant leading terms, right? So in other words, the limit of this rational function as x approaches plus or minus infinity is exactly the same as the limit of the ratio of only the leading terms, right? To me, that just seems like a simpler way to think about it. You don't have to remember any rules that way. And then if I simplify this, the ratio of the leading term simplifies to 3 over x, and as x goes to infinity, that obviously goes to 0, doesn't it? Right? Okay, so we get a horizontal asymptote then. That just tells us our horizontal asymptote is y equals 0, is the x-axis. Okay? All right, so now what? We need to do some derivatives then. What about vertical asymptotes? Are there any vertical asymptotes here? Caleb, any vertical asymptotes for this function?
I think are -1 and 1 those vertical asymptotes?
They are, right, because those are unique zeros of the denominator, right?
Yes.
Okay, so we know that we have vertical asymptotes at x equals plus or minus 1. Okay, so we got lots of asymptotes. Now we need to do some calculus. So let's differentiate. And we've just got to use quotient rule, right? So we get x squared minus 1 times the derivative of the top, which is just 3, minus high d low. So 3x times the derivative of the bottom is just 2x divided by the bottom squared. Okay, and we can simplify that. Anything I can do there that's handy? Well, yeah, there is. So if I distribute the 3, I get 3x squared minus 3 minus 6x squared. So I end up with minus 3x squared minus 3. Is that right? I think it is. Yeah. Over x squared minus 1 squared. And if I factor out a negative 3 on the top, I get negative 3 times x squared plus 1 divided by x squared minus 1 squared. Is that right? Everybody see any mistakes there? Give me a thumbs up if that looks right to you. Okay, so are there any zeros for the first derivative then? Any zeros for the first derivative? No? Agreed? Top is never 0. Are there any critical numbers where the first derivative is undefined? Okay, what are the critical numbers where the first derivative is undefined? Type them in chat if there are any. We're just looking for all the critical numbers of the first derivative, right? So where it's undefined or equal to 0. Okay, so negative 1 and 1, I've seen negative 1 and 1, I'm seeing a 1. Okay, and I get that because that's where the second derivative, where the denominator is 0, right? Okay, but keep in mind, critical numbers can only exist where the function is defined, right? So are those actually critical numbers? No, function's not defined there. So in the domain of the function, there are no critical numbers. So we have no extrema on this thing, okay? Second derivative. So how about if we just go from here? We'll use that version right there. Okay, so if I just differentiate using the quotient rule, I'm going to get x squared minus 1 squared times the derivative of the top, which is negative 6x, minus the top times the derivative of the bottom. Now that's chain rule, right? I've got hand squared, so I get 2 hand to the 1 minus the derivative of hand is 2x divided by the bottom squared. Well, x squared minus 1 squared squared is just to the 4th power. Okay, now can we factor out some common factors? Looks like it, doesn't it? Look, I've got like bases on the top. I can factor out an x squared minus 1 from the top. And I can factor out, how about if I factor out I could factor out a 2x also. How about a negative 2x? What's that leaving me with then? So here's my minus sign. What am I left with from the first term? If I take out an x squared minus 1, I've took taken one of those away. I've got one left. Factored out a negative 2x, leaving me with a positive 3. So I've got 3 times the quantity x squared minus 1. Everybody good with that from the first term? Okay, this is where it'd be nice to give me, if you can, flip your camera on and give me a thumbs up when you're ready, when you're good to hear, so I know that. Okay, I'm getting lots of thumbs up. Okay, I'm gonna move on then. So I factored this out of the second term. Now what's that giving me? So if I factor out a negative 2x, so that's gone, and I'll go ahead and just do this because I took that negative out, right? So now what am I left with? 2 times 3x squared, so I've got a 6x squared that I'm subtracting, and I'm going to distribute that negative, and I'm subtracting a 6. All over x squared minus 1 to the 4th, but I can cancel a factor vertically, like so. Oops. And now I get what on the top? So I get negative 2x times, what happens if I combine all this stuff? 3x squared minus 6x squared is negative 3x squared. And here I'm getting minus 3 minus 6. So minus 9, is that right? I think that's right. Man, I feel like I think that's right. So why didn't I do this? Make all those positive. Okay, give me a thumbs up if you agree with me on that one. Andy, what did I do wrong?
Well, I just have a question. Can you factor a 6 out of the x squared minus 6, and then you can factor it out again, cancel, make it like a squared on the bottom?
Oh, I see what you're saying. Factor a 6 out of that. Yeah, what did I do? So something's goofy there, huh? Oh, no, I can't, because look, if I factor no, I can't. I see what you're saying, but I can't because look, this is a negative 6x squared minus 6. If I factor a negative 6 out of this, I'm going to get an x squared plus 1 from this guy. Okay, makes sense? Okay, so now I need thumbs up, thumbs down. Are we okay with that, or did I do it right? Everybody agree? You see any problems? Okay, so zeros, there it looks, we get no zeros of the denominator that are in the domain, but there is a 0 of the numerator, isn't there? I get x equals 0 is a 0 of the second derivative. Everybody agree? Okay, so let's make our table. Okay, so we had positive and negative 1 were our vertical asymptotes, right? Those are values where the function is undefined. So these are vertical asymptotes. We can just put a line down there. So we know those are vertical asymptotes. We had a 0 of the second derivative at 0. So what do we need to do here? And we know we have a horizontal asymptote. Let's do this too. We can write it this way. So if we take a limit as the function as x approaches negative infinity, y was 0, and the limit as x approaches positive infinity is 0. So we can see we get horizontal asymptotes there. Okay? And if I start to graph this thing, those asymptotes really help with the graph. Oh, what's going on here? Oh, never mind. Okay, I guess I have to go to the next page to graph this thing. There's my horizontal asymptote. There's a vertical asymptote. There's a vertical asymptote, right? A lot of asymptotes. What do we need to do? Where do we need to pick some test points? What do you think? Andy, where should I pick some test points?
Can you pick them on the either side of 0?
Yeah, okay, so I got to go, and I have to pick them between the vertical asymptotes and 0, don't I? So something like, for example, we could pick like negative 1/2 and 1/2. And I'm just evaluating the second derivative there. So at positive 1/2, what do we get? We get, let's do it this way, f double prime of 1/2 equals, on the top we're going to get positive times positive divided by 1/2 squared is 1/4 minus 1. That's negative cubed is negative, right? So positive over negative, it's giving us negative, isn't it? We get a negative second derivative there. What about at negative 1/2? If I did the same thing at negative 1/2, the bottom is going to stay negative, isn't it? That factor is always positive, but this one becomes negative. So it's going to look like that. So it does change concavity at 0. Okay, so we know then, let's go ahead and plug 0 into our function. What do we get if I evaluate this at 0? Well, I just get 0. So at the point 0, 0, I have an inflection point coupled with my vertical asymptotes. I know what this graph looks like. Right? How would I graph that? If I know I've got a point at 0, 0, and it was, what was the concavity? It was negative to the right and positive to the left. What does this thing have to look like there then? If it's concave down to the right, up to the left, only one thing it can do, right? Doesn't it have to do? Doesn't it have to do that? Everybody see that? Because it has to stick to those asymptotes, right? Give me a thumbs up if that makes sense. You see how much those asymptotes help us? They really help. Now, what about out here on the other sides? So there's only two things it could possibly do, right? Either this function is going to be doing this, because there are no extrema, right? So either it's doing that or it's doing that. Same thing over here. We have to just figure out which one is it. So we could work we could work in any column we want to, or any row we want to here, whichever one seems easiest for the functions. What if we look at the first derivative? The first derivative, the top is always negative, agreed, and the bottom is always positive because it's being squared. So the first derivative is always negative. What does the graph have to be doing then? Right? It's got to be, if it's always negative, it has to be decreasing. Let's look at this part over here. If it's always decreasing and it has to adhere to these two asymptotes, doesn't it have to be doing that? Everybody agree? Has to, right? Okay, on the other side, if it's always negative and it's got to stick to this horizontal asymptote and that vertical one, it's got to do that, right? Now, we know that for a variety of reasons, though, too, because we already knew that it has odd symmetry. So we know this thing's also got rotational symmetry about the origin. So whatever the right half of this function looks like to the right of x equals 0, if I spin this thing 180 degrees, it's got to line up with the left side. So that works, doesn't it? Okay, we could have done this in the second derivative row of our table. If we went down to the second derivative, we know that if I were to pick a test point down here, for example, at like, we'll just pick like 10 or something, right? So if it's a negative 10. If I pick 10, the sign of the second derivative at 10 is going to be positive times positive divided by positive, so it's positive. Well, there it is. If it's going to be stick to these asymptotes and be concave up, that's the only place it could be. By the odd symmetry, then it's got to look like this over here, right? Or if I wanted to pick a test point, I could have done that too. It all works. If I plug negative 10 in, I'm going to get negative times positive over negative. Yeah, hold it. No, getting negative. Yeah, I'm getting negative times positive over positive. So it's negative, right? Makes sense. So it's concave down. Okay? How about that? All that stuff is contained in that table. That's pretty cool. You get all that information in that table. Okay? Thumbs up, thumbs down. How we do? Give me 1 to 5 on that one. Okay? I don't know if we're going to get through this, but I want to look at one more. And the reason I want to here is because we haven't looked at one where the top is one bigger than the bottom. So this is going to remind us about something. We can do a lot of this. We can zip through this. We've already done functions similar to this. Would you agree that the symmetry on this one is going to be odd? Top is odd, bottom is even. So overall, it's going to be odd. So we know we're getting odd symmetry, or I can just do my test for symmetry. The domain is x cannot equal plus or minus 1. Those are vertical asymptotes, aren't they? Those are zeros of the bottom, but not the top. We get odd symmetry. Now, what about, before we jump into the calculus here, what about the limits at plus or minus infinity? Okay, this is a case where if I take the limit of this function, the top is bigger degree than the bottom this time, right? So the top is going to grow faster. So there is no horizontal asymptote here, agreed? Okay, but what is there? Okay, if the top is exactly 1 degree higher than the bottom, then this is going to give us a slant asymptote or an oblique asymptote, whatever you want to call it. And we have to just divide this out, right? So how can we divide this out? Let's remind ourselves how we do this. It's been a little while since we've done this, but this is pretty good stuff to review. So we could divide this out using long division. That's fine. We could also divide this out using synthetic division too, if we wanted to, right? Take your pick. How about if we just let's use long division on this, because why would we gravitate to long division on this? Yeah, right, because you can only use synthetic division where you have linear factors of the denominator, right? And so you could make it work, but it's a little awkward to do. I don't want to take the time to do it today. Maybe later on we'll come back and I'll show you. I'll remind you how you could use repeated synthetic division on this. But for now, let's just use long division. So if we divide x squared minus 1 into x cubed, which is really x cubed plus 0x squared plus 0x plus 0, right? What do we get here? So x squared divides into x cubed how many times? X times. Remember, that's always how we do long division. We're dividing the leading term in the denominator into the leading term in the numerator. In other words, x times what is x cubed? X. So I distribute the x. X times x squared is x cubed. X times -1 is negative x. And now I'm going to subtract vertically, right? So it's a good idea to put this in parentheses and put a negative out front. So you remember you're subtracting the whole quantity. What's that give us? These cancel, of course. X cubed minus x cubed cancels. 0 minus negative x gives me a positive x, which is my remainder, because x squared won't divide into that. And so what's this equal to then? This is equal to x plus x plus my remainder of x, and it remains over my denominator, right? And so now if I take the limit of this, the limit of x plus x over x squared minus 1, as x approaches plus or minus infinity, look what happens. I get this rational function here where the bottom is bigger than the top. So that rational function in the infinite limits, as we approach plus or minus infinity, that goes to 0. And so I'm just stuck with my limit is equal to x. So my slant asymptote is the line y equals x. Okay, and that's where we'll leave off for today. So my slant asymptote, y equals x. Okay? All right, keep going on this stuff. We got one more day of this. I want to go through a few more of these, and then we're done with this section. Okay? This is a huge section. There's a lot going on. Have a great day. I'm here after school if you need me. Natalie, email me. Okay?